How do you force your mind to learn anything you want? The question itself contains a fundamental misconception about what learning actually is. You cannot force your mind to learn the way you might force a door open or compel an object to move. The brain is not a passive container waiting to be filled with information. It's a physical system, a network of approximately 86 billion neurons connected by trillions of synapses, and it operates according to specific biological and physical principles. If you want to understand how learning works, you must first understand what happens in your brain when you learn, and why certain approaches succeed while others fail. Let's start with what learning is at the most fundamental level. Learning is the modification of synaptic connections between neurons. When you learn something, you are physically changing the structure of your brain. Neurons communicate through synapses, junctions where chemical signals pass from one neuron to another. When a neuron fires repeatedly in response to a stimulus, the synapse connecting it to the next neuron strengthens. This strengthening makes it more likely that the same pattern will fire again in the future. This is the physical basis of memory and learning. The phrase often used is neurons that fire together wire together, which captures the essential mechanism. Learning is not abstract. It is the literal rewiring of neural circuits through repeated activation. Now here is the critical insight. This rewiring happens automatically when certain conditions are met. You cannot choose to strengthen a synapse directly, any more than you can choose to digest food faster by thinking about it. Synaptic strengthening occurs as a consequence of neural activity patterns. What you can control are the conditions that produce those patterns. This is where most people go wrong. They try to force learning through willpower or repetition without understanding the underlying mechanisms. They treat their brain as if it were a hard drive that stores whatever you put into it. But the brain is not a storage device. It is a prediction machine, evolved to detect patterns, form models of the world, and anticipate future events. Learning occurs when your brain updates its internal models in response to new information. Consider what happens when you try to memorize something by rote repetition. You read a fact, then read it again, then again. This approach feels like learning because you are exposing yourself to the information repeatedly. But examine what is actually happening in your neural circuits. Each time you passively read the same information, you activate roughly the same neural pathway. But if there is no challenge, no difficulty, no prediction error, the synaptic changes are minimal. Your brain allocates resources to strengthening connections based on relevance and surprise. If information arrives exactly as expected without discrepancy, the brain has no reason to update its model. This is why passive reading produces weak learning. There is no error signal driving synaptic modification. The brain learns most effectively when it makes predictions and receives feedback about whether those predictions were correct. This is not a pedagogical preference. It is how the neural machinery functions. When your brain predicts one outcome and experiences another, a prediction error occurs. This error generates neural signals that trigger synaptic plasticity, the process by which connections strengthen or weaken. Dopamine neurons, for instance, respond to unexpected rewards by releasing dopamine throughout the brain, which modulates synaptic plasticity in regions involved in learning. The error signal tells your brain that its current model is insufficient and needs updating. Without prediction errors, learning is slow and inefficient. This leads to a specific testable claim about how to learn effectively. You must engage in active recall. Instead of passively reviewing material, you must attempt to retrieve it from memory. This retrieval attempt forces your brain to make a prediction about what the correct information is. When you check whether your retrieval was accurate, you generate a prediction error if you were wrong, and you confirm your model if you were right. Either way, the active retrieval strengthens the memory far more than passive review. This has been demonstrated in hundreds of experiments. Students who test themselves learn more than students who simply reread material, even when the testing is difficult and produces many errors. The difficulty is not a bug. It is the feature that drives learning. Let's examine why this works at the neural level. When you attempt to recall information, you activate the neural pathways associated with that memory. This activation itself strengthens the synapses in that pathway through a process called long-term potentiation. If your recall is successful, the pathway is reinforced. If your recall fails, and you then review the correct information, the contrast between your incorrect prediction and the correct answer creates a strong error signal, which drives even greater synaptic modification. The struggle to retrieve information is what creates the conditions for lasting learning. Ease is the enemy of learning. If retrieval feels easy, you are likely activating strong, already established pathways that do not need further strengthening. If retrieval feels difficult, you are forcing your brain to work harder, which is precisely what drives plasticity. Now we must address a deeper question. If learning requires difficulty and prediction errors, how do you decide what to learn and when? Your brain has limited resources. Neurons require energy. Synaptic plasticity is metabolically expensive. Your brain cannot strengthen every possible connection simultaneously. It must allocate resources based on what matters. This is where attention becomes critical, and attention is not what most people think it is. Attention is the mechanism by which your brain selectively processes certain information while ignoring the rest. At any given moment, your sensory systems receive far more data than your brain can fully process. Visual information alone arrives at a rate of millions of bits per second. Your brain cannot analyze all of it in detail. Instead, attention acts as a filter, prioritizing certain inputs for deep processing while suppressing others. What determines what gets prioritized? Relevance to your current goals and unexpected or novel information. Your attentional system is controlled by networks in the prefrontal cortex and parietal cortex, which receive input from systems that evaluate salience and goal relevance. Here is the key insight. You can control your attention, and by controlling attention, you control what your brain learns. When you focus attention on specific information, you increase the neural activity in the circuits processing that information. This increased activity makes those circuits more likely to undergo synaptic strengthening. Attention amplifies learning. Conversely, if your attention is divided or diffused, the neural activity is spread thinly across many circuits, and none of them receive sufficient activation to drive strong plasticity. This is why multitasking impairs learning. You are not actually processing multiple streams of information simultaneously. You are rapidly switching attention between them, which means none receive sustained, focused activation. The practical implication is straightforward. To learn effectively, you must eliminate distractions and focus your full attention on the material you want to learn. But focus alone is insufficient. You must also ensure that the material engages the prediction error mechanisms we discussed earlier. This means you cannot simply stare at information and hope your brain absorbs it. You must interact with it. You must ask yourself questions about it, attempt to explain it, try to apply it to new situations. Each of these activities forces your brain to make predictions, and each prediction creates an opportunity for learning through error correction. Flaus consider spacing and interleaving, two principles that emerge directly from understanding neuroplasticity. Spacing refers to distributing learning over time rather than cramming it into a single session. Why does spacing work? Because synaptic strengthening has a time course. When you activate a neural pathway, the synapses involved undergo changes that persist for hours to days. If you attempt to reactivate the same pathway after a delay, you force your brain to retrieve the information from a partially consolidated state. This retrieval strengthens the memory further and triggers additional consolidation. If you practice the same material repeatedly in immediate succession, you are activating pathways that are already in a heightened state of excitability, so each additional repetition adds less benefit. Spacing creates the optimal challenge. The pathway has weakened slightly due to time, so reactivation requires effort, which drives stronger learning. Interleaving refers to mixing different types of problems or topics during practice, rather than blocking them into separate sessions. This seems counterintuitive. Most people prefer to practice one type of problem until they master it, then move to the next type. But interleaving produces better long-term learning, and the reason relates to discrimination and pattern recognition. When you practice only one problem type at a time, your brain does not need to identify which type of problem it is. The context tells you. But in real-world situations, you must first recognize what kind of problem you are facing before you can solve it. Interleaving forces your brain to practice this recognition step. It also creates more varied prediction errors because the context keeps changing, which strengthens your ability to apply knowledge flexibly rather than in a rigid context-dependent manner. Now let's address the concept of understanding versus memorization. Many people treat these as separate goals, but they are not. Understanding is a specific type of memory, a memory of relationships and principles rather than isolated facts. When you understand something, you have built a mental model, a network of interconnected concepts that allows you to make predictions and inferences. This mental model corresponds to a network of interconnected neural circuits. The more connections in the network, the deeper your understanding. Memorization without understanding means you have activated a small isolated set of neurons without connecting them to broader networks. This is why rote memorization is fragile. If you forget one element, the entire memory can collapse because there are no alternative pathways to retrieve it. To build understanding, you must actively construct connections between new information and what you already know. This is called elaborative encoding. When you encounter a new concept, ask yourself how it relates to concepts you already understand. Generate examples. Think of situations where the principle applies and where it does not. Each of these mental activities creates new synaptic connections, integrating the new information into your existing knowledge network. The more connections you create, the more robust and flexible your understanding becomes. This is not a vague pedagogical suggestion. It is a direct consequence of how neural networks store and retrieve information. Redundant pathways make retrieval easier and make knowledge more accessible in diverse contexts. We need to examine the role of sleep in learning because this is where many people's understanding completely breaks down. Sleep is not rest in the sense of inactivity. During sleep, your brain is extraordinarily active, and much of that activity is dedicated to memory consolidation. Consolidation is the process by which temporary fragile memories stored in the hippocampus are gradually transferred to the cortex for long-term storage. This transfer happens primarily during sleep, especially during slow-wave sleep and rapid eye movement sleep. Here is what happens at the neural level. During the day when you learn new information, your hippocampus rapidly forms a temporary memory trace. The hippocampus is specialized for fast learning, but it has limited capacity. During sleep, the hippocampus replays these memory traces, reactivating the same neural patterns that were active during learning. This replay occurs in coordination with slow oscillations in the cortex, which create windows of heightened plasticity. The synchronized replay allows the cortex to gradually strengthen the synaptic connections that encode the memory. Over time, the memory becomes independent of the hippocampus and resides in distributed cortical networks. This is why sleep deprivation impairs learning so severely. Without adequate sleep, the consolidation process is disrupted, and memories that seemed solid the night before become inaccessible. The evidence for this is overwhelming. Studies using neural recordings in animals show that neurons that fired together during learning fire together again during sleep, in the same sequential patterns. Studies in humans show that sleep improves performance on memory tasks, and that the amount of improvement correlates with the amount of slow-wave sleep. Depriving subjects of sleep after learning impairs their memory, while allowing sleep preserves it. This is not subjective or anecdotal, it is measurable, reproducible neuroscience. The practical implication is that if you want to learn effectively, you must prioritize sleep. Studying late into the night at the expense of sleep is counterproductive. You may expose yourself to more information, but without sleep to consolidate it, much of that information will not transfer into long-term memory. The optimal strategy is to study, sleep, then review. The review after sleep reinforces the consolidation that occurred overnight and integrates the new knowledge more deeply. Now let's discuss motivation and its relationship to learning. Motivation is often treated as a psychological state, something you either have or do not have. But motivation has a neural basis, and understanding this basis reveals how to harness it. The brain's reward system, centered on structures like the ventral tegmental area and nucleus accumbens, releases dopamine in response to rewards and reward prediction. Dopamine is not pleasure. It is a signal that something important is happening, something worth paying attention to and learning from. When you anticipate a reward or achieve a goal, dopamine release enhances plasticity in the circuits active at that moment, making learning more efficient. This explains why learning is easier when it is intrinsically rewarding. If you find a subject inherently interesting, your brain's reward system activates when you engage with it, releasing dopamine that facilitates learning. But if you find the subject boring or irrelevant, the reward system is silent and learning becomes harder. You can, however, create artificial reward signals. Breaking your learning into small, achievable goals and rewarding yourself when you reach them can activate the reward system and enhance learning. This is not manipulation. It is using your brain's natural learning mechanisms deliberately. Another critical factor is emotion. Emotionally significant events are remembered more vividly than neutral events because the amygdala, a brain structure involved in processing emotion, modulates memory consolidation. When something evokes strong emotion, the amygdala enhances the consolidation of that memory in the hippocampus and cortex. This is why you remember where you were during major life events, but forget most ordinary days. The emotional salience tagged the memory as important. You can leverage this by connecting new information to emotionally meaningful contexts. If you care about why you are learning something, if it connects to your goals or values, your brain will prioritize it. Now let's address the concept of chunking, which is fundamental to expert learning. Your working memory, the system that holds information temporarily while you manipulate it, has a limited capacity. It can hold roughly 4 to 7 items simultaneously. This seems like a severe constraint, but experts circumvent it through chunking, the process of grouping individual elements into larger, meaningful units. A chess master looks at a board and sees patterns, configurations of pieces that have strategic significance. A novice sees individual pieces. The master's working memory holds the same number of chunks, but each chunk contains far more information because it represents a familiar pattern. Chunking occurs through practice and exposure. As you repeatedly encounter certain patterns, your brain learns to treat them as single units. The neural correlate is the formation of higher-level representations in which a single neuron or small group of neurons responds to an entire pattern rather than individual elements. This is hierarchical processing. Lower levels of the neural hierarchy process basic features. Higher levels integrate those features into more abstract representations. Learning deepens as you build these hierarchies, allowing you to think in terms of concepts and principles rather than isolated facts. Let's now synthesize these principles into a coherent understanding of how to learn anything effectively. Learning is a physical process of synaptic modification driven by neural activity. To learn efficiently, you must create the conditions that drive strong, lasting synaptic changes. This requires several elements working together: focused attention to amplify neural activity in relevant circuits, active retrieval to generate prediction errors and strengthen memory traces, spaced repetition to optimize consolidation over time, interleaving to build flexible, generalizable knowledge, elaborative encoding to integrate new information into existing networks, adequate sleep to allow consolidation to occur, and motivation to engage the brain's reward systems that enhance plasticity. Notice that none of these principles require special talent or innate ability. They are all strategies that work because of how the brain functions. This reveals something profound. Learning capacity is not fixed. The idea that some people are naturally good learners and others are not is largely a misconception. What varies is not the fundamental capacity to learn, but the strategies people use and their beliefs about learning. If you believe that learning is about inherent intelligence, you will avoid challenges because failure threatens your self-concept. If you believe that learning is about effective practice, you will embrace challenges because difficulty is where learning happens. This perspective is supported by research on neuroplasticity, the brain's ability to reorganize itself throughout life. It was once thought that the adult brain was relatively fixed, that learning was primarily for children. We now know this is false. Adult brains retain substantial plasticity. You can learn new skills, acquire new knowledge, even grow new neurons in certain brain regions throughout your life. The brain adapts to the demands placed on it. If you consistently challenge your brain with difficult, effortful learning, it will adapt by strengthening and refining the circuits involved. If you avoid challenge and stick to what is easy, those circuits will not develop. The implications extend beyond individual learning strategies. They touch on how we understand knowledge itself. Knowledge is not something separate from the knower, stored externally and transferred into the mind. Knowledge is the structure of neural networks, the patterns of connectivity that allow you to perceive, predict, and act. When you learn physics, you are building neural circuits that respond to physical patterns in the world. When you learn mathematics, you are constructing abstract representational systems in your cortex. Your knowledge is quite literally a part of your physical brain structure. This is why forgetting occurs. If you do not use a piece of knowledge, the synaptic connections encoding it weaken over time. Use it or lose it is not a metaphor. It is a description of synaptic maintenance. Here is the deepest point. Learning is not about acquiring a static collection of facts. It is about continuously refining your internal model of the world so that you can make better predictions and take more effective actions. This process never ends. Every experience is an opportunity to update your model, to strengthen accurate predictions and revise inaccurate ones. The brain is designed for this. It is a learning machine, constantly sampling the environment, comparing predictions to outcomes, and adjusting its internal parameters. You do not need to force this process. You need to align with it, to create conditions where the natural learning mechanisms operate effectively. Consider what this means for mastery of a subject. Mastery is not the accumulation of facts, but the development of richly interconnected neural networks that allow you to see deep patterns, make accurate predictions, and generate novel solutions. An expert physicist does not simply know more facts than a novice. The expert's brain has different structure. Neural circuits in the expert's cortex have been refined through years of practice to respond to abstract physical principles. The expert sees a problem and immediately recognizes its deep structure because their neural networks encode that structure directly. This takes time and sustained effort, but it is achievable because the brain will build whatever circuits you consistently use. The final insight is that learning how to learn is itself a learnable skill. The principles I have described, active recall, spaced repetition, interleaving, elaboration, these are strategies that improve with practice. As you apply them, you get better at judging what works, at calibrating difficulty, at recognizing when you truly understand something versus when you only think you do. Metacognition, the ability to monitor and control your own thinking, relies on prefrontal circuits that develop through use. The more you practice effective learning strategies, the more automatic and efficient they become. So the answer to the original question is this: you do not force your mind to learn. You cannot. The brain is a physical system that operates according to laws. What you can do is understand those laws and work with them. You can create the conditions that activate learning mechanisms: attention, prediction errors, retrieval practice, consolidation through sleep, emotional engagement, and sustained deliberate practice. When you do this consistently, learning happens naturally, not because you forced it, but because you aligned your behavior with how your brain actually works. This is not a trick or a shortcut. It is simply respecting the reality of what you are, a biological learning system shaped by evolution to adapt and improve. The capacity is already there. You only need to use it correctly.